Welcome back, everybody, to another deep dive. And today we're going to be taking a look at something really interesting.
Yeah.
We are going to be looking at antimatter,
Antimatter.
and we're going to be looking at the life and work of the guy who first predicted it, Paul Dirac.
That's right.
Now, our listener sent in some excerpts from a biography about Paul Dirac,
Okay.
focusing on his early life and work, and that's what we're going to be going through today.
Sounds good.
Now,
I think.
for people who aren't familiar with this,
Yeah.
antimatter, right? This sounds like something out of Star Trek.
Right.
It's just this crazy sci-fi concept, but this is a real thing
Absolutely.
that exists, and Paul Dirac was one of the first people to predict it.
Yeah, he was a real pioneer.
And he was kind of an eccentric guy, as I understand it.
Oh, yeah. Very much so.
So we'll
But
talk about
his
work, but also a little bit about him personally.
Very quiet, very brilliant mathematically,
Yeah.
but a little bit of a strange character.
I was reading that he didn't like to be called Professor Dirac.
Right.
He preferred Mr. Dirac.
Yeah, he preferred Mr. Dirac. He thought Professor was a bit too highfalutin.
Now,
Physics,
to
life,
give
data,
people
like-
some background, because you can't just jump into antimatter.
Right.
You need to understand the context of physics at the time when he was working.
Yeah.
So can you set the stage for us a little bit? Like, what was happening in physics at the turn of the 20th century?
At the turn of the 20th century, they pretty much thought they had it all figured out in terms of physics.
Okay.
They had what was called classical physics.
Right.
You had Newtonian mechanics, you had Maxwell's equations for electromagnetism,
Right.
and they thought, okay, we got it all figured out.
Right. It's
And
all wrapped up in a nice, neat package.
it was all pretty much wrapped up.
Yeah.
But there were a few little,
Little inconsistency.
inconsistencies. Yeah, little things that weren't quite right. And
That always seems to happen, right? That happened with Newtonian mechanics, right?
I
They
didn't
thought
know
everything
this.
was going great, and then Einstein came along and said,
right.
nope. Yeah, you got to think about it a different way.
Yeah.
Yeah, so they had these, little inconsistencies, and what that led to was these two revolutionary theories that sort of came out of that.
Okay.
And one was relativity, and the other was quantum mechanics. And these
Right.
two theories sort of changed our whole
Yeah.
understanding of the universe.
Yeah, it was a complete paradigm shift. Right. Like they really
Exactly, yeah, complete paradigm shift.
turned things upside down.
And it was right around that time that Paul Dirac sort of arrived on the scene.
Oh,
So
right.
he was sort of right at the cutting edge of all of this change,
Okay.
this upheaval in physics.
Yeah. And
Yeah.
the biography, as I said, focused a lot on his early life. So let's talk about that a little.
Yeah, sure.
What are some of the interesting points about Dirac's early life? I mean,
Mhm.
well, one of the interesting things is that even as a child, he showed an aptitude for geometry
Okay.
and technical drawing,
Interesting.
more so even than for math initially.
Right.
But this ability to sort of visualize complex problems, I think, is what really
Yeah.
helped him later on when he was working in theoretical physics.
It's like he was training his brain
Yeah.
to think about these things
Exactly.
in a very visual way.
Yeah, and that's how he thought about things very visually.
Okay.
And another interesting thing about his upbringing was it was very rigorous.
Okay.
His father was a French teacher,
Okay.
and he insisted that they only speak French at home.
Wow.
And some speculate that this is what led to Dirac being so quiet and reserved,
Really?
because
Yeah.
he wasn't as free with his English.
Right.
Oh, yeah.
Interesting.
Oh,
Yeah,
sorry.
because he wasn't practicing it all the time.
Yeah, exactly.
So how did he go from a guy who was, really into shapes
Right.
to quantum mechanics?
Well, his path wasn't entirely straight.
Okay.
He first studied electrical engineering at the University of Bristol.
Engineering.
Yeah, electrical engineering.
Okay.
And, not an obvious path to
Yeah.
theoretical physics, but
Yeah.
but he did that. And, for a while, it looked like he might pursue a career in engineering.
Okay.
But then the economic hardships in post-World War I England,
Right.
it was tough to find work.
Yeah.
So he went back to university.
Okay.
This time he studied mathematics.
Okay.
And then eventually he ended up at Cambridge to study physics.
Okay. So a little bit of a roundabout path.
A bit of a roundabout path. Yeah, but
Yeah.
luckily for
Yeah.
physics, he
Yeah.
ended up there.
Yeah.
Yeah.
So he's immersed in this new world of quantum mechanics. How does he react to this? I mean, this is
Again,
pretty strange stuff.
it's weird stuff.
Yeah.
And the biography suggests that he was initially more interested in relativity.
Okay.
But he was assigned to work with Ralph Fowler, who was an expert in quantum mechanics.
Okay.
So he was sort of thrust into this world.
Okay.
But despite that initial, disappointment maybe,
Right.
he jumped right in
Okay.
and really made a name for himself very quickly.
So it wasn't love at first sight.
Not quite, no.
Yeah.
But he was a quick study.
Yeah.
Yeah.
Okay. What are some of his early contributions then?
Well, one of his early contributions was he was trying to make sense of Heisenberg's matrix mechanics.
Okay.
Now, matrix mechanics is incredibly abstract.
Yeah, I remember trying to learn about matrices, and
It's tough.
it's a lot of numbers, and it's not very intuitive
Right, exactly. And
to think about, electrons as these
no,
little points, right?
no, it's not intuitive at all.
Yeah.
But Dirac, he had this insight, this really brilliant insight,
Okay.
where he connected these abstract matrices to the world of classical physics.
Okay.
And he did this using something called Poisson brackets.
Poisson brackets.
Now,
Okay.
you might remember from classical physics that Poisson brackets,
Trying to remember.
yeah, they're a way of describing how quantities change over time.
Right. So like how
Yeah, so you could use Poisson brackets to describe,
like a planet.
the evolution of a planet's orbit or something like that.
Right. Sure.
It's a mathematical tool.
Yeah.
And what Dirac realized was that these same mathematical tools that are used in classical physics
Right.
could be used to bridge the gap between classical physics and quantum mechanics.
Okay.
So he made it,
That's brilliant.
he made it understandable
Yeah.
to physicists who were steeped in this classical way of thinking.
Right. So he wasn't just sort of recreating what Heisenberg was doing. He was taking it and putting it into a framework that people could actually understand.
Exactly.
That's fantastic.
Yeah, he's giving it context.
Okay.
And what's even more remarkable is that he did all of this independently of Heisenberg and Born and Jordan.
Wow.
So there were like all of these people at the same time working on the same problem.
Yeah. It really seems like there was just so much energy focused on this.
There was, it was like a race
Yeah.
to unlock these secrets of the quantum world.
Okay.
Yeah.
But it wasn't just one race, right? Like it wasn't
Yeah.
just one group of people going down one path. This was like
No, there were different,
multiple approaches.
multiple theories.
Yes, exactly.
Okay.
And, this brings us to another interesting character in the story,
Okay.
Erwin Schrödinger and his wave mechanics.
Wave mechanics. Okay.
Yeah.
I remember a little bit about that.
Yeah, no, wave mechanics was a much more
Yeah.
intuitive way, I think.
Kind of visual.
Yeah, much more visual
Yeah.
than Heisenberg's abstract matrices.
Right. Because instead of thinking about electrons as these little particles, you're thinking about them as these waves spread out in space.
That's right, spread out over space.
Yeah. That has always been a fascinating
Yeah,
concept to me, this whole wave-particle duality thing.
absolutely. Yeah, and, and it defies our everyday intuition of how things work, but in the quantum world...
That's how things behave.
Yeah, but Dirac had some problems with this, right?
You did.
He wasn't totally satisfied with wave mechanics.
Yeah, he wasn't entirely satisfied.
Why is that?
He was a purist.
Okay.
He thought there should be a single mathematical framework
Okay.
that could encompass both matrix mechanics and wave mechanics.
So he was looking for the grand unifying theory.
He wanted a single elegant description.
Okay.
And he wasn't content with having these two different pictures,
I've got it.
even though they both seemed to work.
So this is what's driving him, right?
This is his quest.
This quest for this fundamental description.
Exactly, this quest for a deeper understanding.
And this is ultimately what leads him to antimatter, right?
Yeah, it does.
Okay. We'll save that for next time.
Yeah, before we get to that, there's another concept that's really important.
Okay.
And that's the wave function
The wave function, okay.
and its probabilistic interpretation.
Yeah, so what is this wave function? I mean,
Okay, so the wave function,
it sounds kind of scary.
yeah, it's a little bit scary, but the way to think about it is this.
Okay.
In the quantum world, we can't know exactly where a particle is
Okay.
or what its momentum is with absolute certainty.
Okay.
It's all about probabilities.
Okay.
So the wave function is a mathematical function that describes
Okay.
the probability of finding a particle in a certain location
Okay.
or having a certain momentum.
So it's not like telling us where it is. It's just,
It's giving us a map
yeah.
of where it might be.
Yeah, like a probability map.
Exactly. Yeah.
Okay.
So it's a little weird.
It is a little weird, yeah.
I mean, it's very different from the way that we think about things.
Yeah, and this whole idea of a probabilistic interpretation
Right.
of quantum mechanics.
It's not deterministic.
It's not deterministic.
It's just probability.
It's all about probabilities.
Okay.
And that was a major departure from classical physics.
Right, and that's something that Dirac really had to grapple with.
Oh, as he was going through all of this.
Yeah, he was trying to make sense of it all.
Yeah.
Yeah.
And this is what ultimately leads him to antimatter.
That's right.
But we'll save that for next time.
We'll save that for next time.
Join us again, and we'll talk about the prediction of antimatter.
Looking forward to it.
Okay, thanks, everybody.
Good, thanks.
All right, so we're back.
Back again.
And last time we left off
Yes.
with Dirac searching for this relativistic equation for the electron
Right.
that could take into account Einstein's theory of relativity.
Exactly.
So where did this search lead him?
Well, it led him to an equation that really revolutionized our understanding of the electron.
Okay.
And also opened up this whole world of antimatter.
Antimatter.
Yeah.
Yeah. Okay, break that down for me.
What?
What is this equation?
So it's called the Dirac equation.
Okay.
And it's a beautiful equation.
Okay.
It combines quantum mechanics and special relativity.
Okay, so this is like the holy grail that everybody was looking for, right?
Yeah, exactly. Yeah.
Yeah.
Something that could describe electrons at speeds approaching the speed of light
Right.
and also behaving according to the strange rules of quantum mechanics.
Okay, so he found it.
He found it.
But I understand there was a little twist.
There was a little twist.
With this equation.
Yeah, this equation had a surprising consequence.
Okay.
It predicted that there should be a particle that was just like an electron, but with a positive charge.
So basically a
positron, exactly.
Which had never been observed before.
No, nobody had ever seen anything like it.
But his math said it should be there.
The math said it had to be there.
Okay, so he wasn't actually like trying to discover antimatter.
Yeah.
It just kind of came out of his
It popped out of the equation.
pursuit of this elegant theory.
Yeah, he was looking for a beautiful equation.
Okay.
And this is what he got.
Wow.
And it had these incredible consequences.
So he was driven by beauty.
He was driven by beauty.
And it led him to truth.
That's right.
Okay.
Yeah.
Now, I understand he had some trouble
Yes.
wrapping his head around
Yeah.
what this all meant.
Absolutely.
And he came up with this idea
Yeah.
of holes in a sea of negative energy electrons.
Yes, the Dirac sea.
What is that all about?
Okay, so Dirac's equation predicted that electrons could have negative energy states.
Negative energy state.
Negative energy states.
Which doesn't really make sense.
It doesn't really make sense in our everyday world.
Right.
You know, energy is always positive.
Yeah.
But in the quantum world, things can get a little weird.
A little strange.
A little strange, yeah.
Okay.
So Dirac was trying to make sense of these negative energy states.
Okay.
And he came up with this picture, this model,
Right.
called the Dirac sea.
So,
And what it is it's like an infinite sea of electrons.
okay.
And they're all occupying these negative energy states.
Okay.
And all of these states are completely filled.
Okay.
So that's the ground state.
All right.
It's like a sea of electrons all packed in.
I'm picturing it and I don't like it.
Yeah, it's a strange picture.
It's a little disturbing.
But here's where the positrons come in.
Okay.
If you were to add enough energy
Okay.
to one of these negative energy electrons,
Right.
you could kick it up to a positive energy state.
Okay.
And what that would leave behind is a hole in the sea.
Okay, so this hole,
This hole.
where the electron used to be,
Yes,
is what we see as a positron.
that's exactly it.
Okay.
So this hole would behave like a particle with a positive charge.
Okay.
And that's what a positron is.
Wow.
Yeah. So antimatter, in Dirac's view, was really just a consequence
Okay.
of this structure of the vacuum itself.
So it's not like some exotic thing that came from
Right.
somewhere else. It's just
It's built into the fabric of reality.
his hole in the sea.
It's pretty wild.
It's pretty wild.
Yeah.
Now, I understand people didn't really buy this at first.
Not at first, no.
It was a little too...
A little too strange.
Okay.
Even for physicists.
Yeah.
Yeah. But then a few years later, something amazing happened.
Okay.
This experimental physicist named Carl D. Anderson
Okay.
was studying cosmic rays.
Right.
These are high-energy particles that come from space.
Okay.
And he was looking at them in his cloud chamber.
Okay.
And what he saw was a particle that behaved just like an electron.
Oh, okay.
But it curved the wrong way in a magnetic field,
Okay.
indicating that it had a positive charge.
So he found a positron.
I found a positron.
Wow.
Exactly.
And that really shook things up.
It did, yeah. It was the first experimental confirmation
Yeah.
of antimatter.
So this idea that seemed so crazy
Yeah,
turned out to be true.
that's right.
And it's all because Dirac was following the math
He was following the math, and he was driven by beauty.
by beauty.
Yeah.
Okay, now, even with the discovery of the positron, this whole Dirac idea
Yeah.
remained a little bit controversial, right?
It did, yeah. As physicists developed a deeper understanding of quantum field theory,
Okay.
the picture shifted a bit.
Okay.
But the essential prediction that antimatter exists...
Right, remain valid.
Okay.
Yeah.
Okay, so the picture changed.
Yeah.
But the prediction...
The prediction is still good.
still good.
Yeah.
And it all goes back to Dirac.
It all goes back to Dirac and his beautiful equation.
Okay.
Yeah.
Now, this idea of the Dirac sea, I mean, are people still working with that model, or is that pretty much been abandoned?
Pretty much been abandoned.
Okay.
Yeah, it was a stepping stone to a more complete understanding.
Okay.
But we've moved beyond that now.
But it was an important step in the process.
It was an important step, yeah.
Okay.
Yeah.
Now, antimatter, right?
Yeah.
Big implications for our understanding of the universe.
Huge implications.
Yeah. I mean,
yeah.
if for every particle of matter,
yeah,
there's a particle of antimatter.
Right.
Why is there so much more matter than antimatter?
That's the big question.
Yeah.
Yeah, where did all the antimatter go?
Right. Because if in the Big Bang, all this matter and antimatter was created, it should have all just annihilated.
It all should have just canceled each other out.
Yeah.
And we wouldn't be here.
So there's something we're missing.
There's some asymmetry, some tiny little imbalance that led to this excess of matter.
Okay.
And that's one of the big mysteries in physics.
Still unsolved.
Still unsolved, yeah.
Okay.
We don't know why we're here.
So Dirac not only opened up this whole new world of antimatter, but also just led to all of these new questions.
Yeah.
Okay, now
about the universe.
Dirac didn't just stop there. He kept going.
Yeah.
And he started working on something called magnetic monopoles.
Magnetic monopoles, yeah. And that was another consequence of his pursuit of mathematical beauty.
Okay.
But this time his starting point was a little different.
Good.
He was fascinated by the fact that electric charge is quantized.
Quantized, what does that mean?
That means that electric charge comes in these little discrete units.
Like the charge of an electron.
Right, so you can't have like half an electron charge.
You can't have half an electron charge, exactly.
Right, okay, I've never really thought about that.
Yeah, it's one of those things you sort of take for granted.
Yeah.
But it's actually really mysterious.
Yeah, like why is it that way?
Why is it that way? Why doesn't charge come in a continuous spectrum?
Yeah.
You know, why these little packets of charge?
Like you can only buy eggs by the dozen.
Exactly, yeah. Why not individually?
Okay.
So Dirac was really intrigued by this.
Okay.
And he thought maybe there's a deeper explanation for this.
Okay.
And what he realized was that if magnetic monopoles existed...
Magnetic monopoles?
Yeah, it would explain this quantization of charge.
Now, what is a magnetic monopole?
So a magnetic monopole is a hypothetical particle that has only one magnetic pole.
Okay, so like a normal magnet has a north and a south pole?
North and south, yeah.
But this would just have one?
Just one. Either north or south, but not both.
Which doesn't make sense.
It doesn't make sense in our everyday experience.
Right.
If you cut a magnet in half, you get two smaller magnets.
Right.
Each with a north and a south pole.
But Dirac's saying that maybe there's this particle out there that just has a north?
Just a north or just a south?
Or just a south.
Yeah.
Okay, and this would explain why charge is quantized.
That's right, yeah.
Okay, now has anyone ever actually seen a magnetic monopole?
No, nobody's ever seen one.
So this is still just
It's still hypothetical.
A theoretical idea.
Yeah.
But if they were found...
If they were found, it would be huge.
Yeah?
It would be a major discovery.
Okay, so this all goes back to Dirac's love of beauty.
Love of beauty, yeah.
He was fascinated by
the
quantization of charge.
Right.
Thought there must be...
Some deeper reason.
Some deeper reason.
Yeah.
And came up with this idea of magnetic monopole.
Yeah, he connected those two things.
Wow. Okay, now, yeah.
We've talked about antimatter. We've talked about magnetic monopoles.
Yes.
But I want to come back to this idea of mathematical beauty.
Okay.
Because this seems to be a recurring theme with Dirac.
Absolutely.
It's like it was driving him.
It was a driving force.
Yeah, he wasn't just looking for equations. He was looking for beautiful equations.
Beautiful equations, yeah.
Why was that so important to him?
Well, for Dirac, beauty wasn't just aesthetics.
Yeah.
It was a signpost to truth.
Okay.
He believed that the fundamental laws governing the universe should be both correct and beautiful.
So almost like nature has this inherent...
Artistic side.
Artistic side.
Yeah.
Okay, and that comes through in the math.
That's right. Okay.
I remember reading that Dirac once visited the University of Moscow.
Yes.
And he was asked to write a phrase on the blackboard that captured his approach to physics.
Yeah.
And he wrote, "A physical law must possess mathematical beauty."
Exactly.
That says it all right. It says it all.
I mean, that's
his whole philosophy.
Yeah.
In a nutshell.
Yeah, it's not enough to just find the equation. It has to be.
It has to be beautiful.
An elegant equation.
An elegant equation.
Okay, now this led to some frustration for him, right?
It did, yeah.
Because as we talked about, with quantum electrodynamics, they were using this technique called renormalization.
Renormalization, right.
And it worked.
It worked, yeah.
But it was kind of messy.
It was a bit messy.
And Dirac didn't like that.
He didn't like it.
Yeah.
He thought it was a bit of a kludge. Yeah.
So
he spent a lot of his later years looking for a more beautiful way.
A more elegant solution.
A more elegant solution, yeah.
Okay.
Yeah.
So there was this tension for him, right?
Yeah, there was a tension between mathematical elegance and experimental validation.
Right, because sometimes they don't agree.
Sometimes they pull in opposite directions.
And Dirac really wanted them to...
He wanted them to come together.
Come together.
Yeah.
Okay, now, even though he wasn't able to resolve that tension completely,
I
mean, his impact on physics is undeniable.
Absolutely.
I mean, he opened up all of these new areas of research.
New avenues of exploration,
He made these predictions that seemed crazy at the time.
Right, antimatter.
And this whole pursuit of beauty really influenced a lot of physicists who came after him.
It did, yeah. It's still an inspiration today.
So as we're wrapping up this deep dive, what do you see as Dirac's most enduring legacy?
I think his enduring legacy is his belief in the power of human reason to understand the universe.
So he really believed that we could...
He believed that math was the key to unlocking the secrets of the universe.
And that beauty was a guide.
Beauty was a guide, yeah.
Okay. And he showed us that you don't necessarily have to just go out and observe things.
Right.
You can actually think your way to...
You can think your way to new discoveries.
New discoveries, just by following the math.
By following the math.
Wow.
Yeah.
Okay, now, Dirac didn't work in isolation.
No.
He was part of a community.
He was part of the community of physicists.
And he built on the work of the people who came before him.
Absolutely.
And the people who came after him built on his work.
That's right. It's a conversation.
It's a conversation.
Yeah, across generations.
Yeah, that's a really nice way to put it.
Yeah.
So Dirac's story is really a story about this ongoing conversation.
It is, yeah.
And the progress of science.
Progress of science, yeah.
Okay.
It's a beautiful thing.
It is.
Yeah.
So as we wrap up, I want to encourage everyone listening to keep that sense of wonder alive.
Absolutely.
To keep asking questions.
Keep asking questions.
Because you never know. You might just stumble on...
You might stumble on the next big thing.
Yeah.
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 Okay.
So thanks for joining us on this deep dive.
Thanks for having me.
Until next time, keep exploring the universe.
Keep exploring.
Keep asking those big questions.
Absolutely.
And we'll see you next time.
See you later.
All right, so we're back and ready to dive into the final part of our deep dive into the life and work of Paul Dirac.
Yeah, we've covered a lot of ground.
We have. We talked about his early life and influences, his groundbreaking equation that predicted antimatter.
Right, and his fascination with magnetic monopoles.
Oh, yeah, those elusive particles with a single magnetic pole.
Still haven't found one of those.
Nope, but the search continues.
It does.
Last time we left off talking about Dirac's discomfort with the concept of renormalization in quantum electrodynamics.
Yes, QED.
Can you remind us what that's all about and why Dirac had such a problem with it?
Sure. So quantum electrodynamics, or QED for short, is the theory that describes how light and matter interact.
Okay, and this was a theory that Dirac himself helped to develop, right?
He did. His relativistic equation for the electron was a key ingredient in formulating QED.
But then, as the theory progressed, physicists ran into some problems.
Yeah, some pretty nasty problems, actually.
And these problems stemmed from these pesky things called infinities that popped up in the equations.
Those infinities were a real headache.
Can you give us an example of where these infinities would show up?
Well, one example is the self-energy of an electron.
Self-energy? What's that?
Basically, it's the energy associated with the electron's interaction with its own electric field.
So even a single electron just sitting there by itself has energy because it's interacting with its own electric field.
That's the idea.
It's kind of like it's playing a game of tug-of-war with itself.
Exactly. And when physicists tried to calculate this self-energy using QED, the answer they kept getting was infinity.
Infinity.
Hmm.
But that doesn't make any physical sense.
It doesn't. An electron can't have infinite energy.
It would be like having a tiny little bomb with the power of a supernova.
Exactly. So physicists knew something was amiss.
So what did they do? Did they just scrap the whole theory and start over?
Not quite. They came up with this really clever trick, a mathematical technique called renormalization.
Renormalization.
Yeah, it basically involves absorbing those infinities into the definition of certain physical constants, like the electron's mass and charge.
So instead of having an electron with infinite mass, you just redefine the mass to take into account the infinite contribution from the self-energy.
Precisely. It's kind of like saying, okay, we know this number should be finite, so let's just adjust things so that it is.
I see, so it's a way of sidestepping those infinities.
In a way, yes. But it's not just an arbitrary fix. Renormalized QED makes incredibly accurate predictions.
So it works in practice, even if it seems a bit ad hoc in theory?
Exactly. It's one of the most successful theories in all of physics.
But you mentioned that Dirac wasn't a fan of this approach.
He wasn't. He saw renormalization as a mathematical band-aid.
A way of covering up a deeper problem within the theory.
Exactly. He believed that a truly fundamental theory should not require these kinds of tricks.
He was looking for an elegant theory, one that was beautiful in its simplicity and didn't need these kinds of ad hoc fixes.
That's right. He spent much of his later career searching for alternative formulations of QED, hoping to find a theory that was both accurate and aesthetically pleasing.
So he was both a pioneer of QED and a critic of its methods.
He was a complex figure, that's for sure.
But his criticism stemmed from this deep desire for beauty and elegance in the laws of physics.
Absolutely. He believed that nature, at its core, was both logical and beautiful.
And that this beauty should be reflected in the equations that describe the universe.
Precisely. And I think this is what makes Dirac such a compelling figure. He wasn't just a brilliant mathematician.
He was also a philosopher of science.
Exactly. He thought deeply about the nature of physical laws, about the relationship between mathematics and reality.
And this quest for beauty, this belief in the elegance of the universe, guided his entire career.
It did. It led him to antimatter, to magnetic monopoles, and to a lifelong search for a more beautiful and consistent theory of quantum electrodynamics.
Even though he didn't achieve all of his goals,
He didn't.
his impact on physics was profound.
Oh, absolutely. He revolutionized our understanding of the electron.
He opened up entirely new avenues of research.
He inspired generations of physicists.
And he left behind a legacy of intellectual curiosity and a deep appreciation for the beauty of the universe.
I think that's a wonderful way to sum up his contributions.
So as we wrap up this deep dive into the life and work of Paul Dirac, I'm left with a sense of awe and inspiration.
You too.
His story is a reminder that the universe is full of mysteries.
And that we have the power to unlock those mysteries.
Through careful observation, creative thinking, and a willingness to follow the math wherever it leads.
Even if it leads to strange and unexpected places.
Exactly. So, to everyone listening, keep exploring, keep questioning, and keep that sense of wonder alive.
Because who knows what amazing discoveries await us out there in the vast expanse of the cosmos.
Maybe we'll even find one of those magnetic monopoles that Dirac predicted.
That would be something.
That was it. It would. All right, that's it for our deep dive into the world of Paul Dirac and antimatter.
Thanks for having me. It's been a fascinating journey.
It has, and thanks to all of you for listening. Until next time, keep exploring the universe and keep asking those big questions.